What if everything you thought you knew about time was just a cosmic sleight of hand? Picture this: the universe as a grand magician, and the arrow of time, the unshakable belief that moments move inexorably forward, is nothing more than an elaborate illusion. For centuries, we've accepted time's one-way flow as a fundamental truth, like gravity or light. But what if the real force behind this illusion isn't some invisible clockwork of the cosmos, but something far more mundane yet profoundly mysterious? Entropy, the gradual unraveling of order into chaos, might just be the hidden puppeteer pulling the strings of our perception. Think about the last time you watched a drop of ink dissolve in water, swirling and spreading until it vanished into uniformity. That irreversible dance is entropy in action, a process that never runs backward. Now, imagine the entire universe as that glass of water, with every moment, every shattered glass, every fading star, every breath you take pushed forward by this relentless drive toward disorder. But here's the twist. What if this isn't time's true nature at all? What if entropy is merely the stagecraft, the smoke and mirrors that make us believe time has a direction, while the deeper reality remains hidden? Scientists and philosophers have wrestled with this question for decades, and the answers they've uncovered challenge everything from the laws of physics to the very nature of existence. This is where the story gets even stranger. The idea that time's arrow might emerge from entropy, a concept born in the study of steam engines and thermodynamics, has led to mind-bending theories about parallel universes, quantum mysteries, and even the possibility that time itself could be an emergent property, a trick of the cosmic deck. Over the next few minutes, we're going to unravel these threads, exploring how the universe might be fooling us all. You'll discover why some physicists believe entropy doesn't just explain time's flow, but might actually create it, how black holes twist this narrative into even deeper paradoxes, and what it all means for our understanding of reality. Buckle up, this journey will take you from the tiniest particles to the vast edges of the cosmos, and by the end, you might never look at a clock the same way again. If time is truly an illusion, then why does it feel so real? We experience every moment as an unbreakable chain: breakfast before lunch, childhood before old age, cause before effect. But here's the cosmic irony. The laws of physics don't actually care which way time flows. At the microscopic level, particles obey equations that work perfectly whether time runs forward or backward. A collision between two electrons looks just as valid played in reverse, like rewinding a film reel. So why does the universe insist on moving in one direction when the rulebook seems indifferent? This is where entropy enters the stage. Think of it as nature's stubborn preference for mess over order. When you scramble an egg, you're not just making breakfast, you're participating in a universal ritual. The yolk and whites will never spontaneously separate again, not because the laws of physics forbid it, but because the odds are astronomically stacked against it. Every possible arrangement of those molecules favors chaos over neatness. That's entropy in a nutshell, the universe's relentless slide toward disorder, and the hidden engine behind time's arrow. But here's where things get really puzzling. If entropy only increases if disorder is the universe's default, then why did we start with such order in the first place? Rewind the cosmic tape to the Big Bang, and you'll find a state of almost unimaginable simplicity, a hot, dense soup where particles were nearly identical. That low entropy starting point is the ultimate magic trick, a wound-up spring that's been unwinding ever since, driving galaxies apart, stars to burn out, and even our own memories to fade. Some physicists argue that without this initial order, time as we know it wouldn't exist at all. So is time just a side effect of entropy's grand parade? The answer might lie in the quantum realm, where particles flicker in and out of existence, blurring the line between past and future, or in black holes where gravity warps space-time so severely that entropy takes on bizarre new forms. One thing's certain, the more we learn, the stranger the illusion becomes. The next time you glance at a clock, remember, you might not be watching time pass, but entropy's sly performance, convincing us all that the show must go forward. Entropy might sound like an intimidating scientific term, but at its core, it's just a measure of disorder, a way to quantify how messy things can get. Think of it like your bedroom. Left to its own devices, it doesn't stay tidy. Clothes pile up, books scatter, and chaos creeps in. That's entropy in action, the universe's quiet insistence that things naturally fall apart unless energy is spent to keep them orderly. Now, zoom out from your bedroom to the cosmos, and you'll see the same rule applies everywhere. From the way milk mixes into coffee to the way stars exhaust their fuel, entropy is the silent force nudging everything toward disorder. This idea isn't just poetic, it's rooted in the hard science of thermodynamics, the study of heat and energy. The second law of thermodynamics states that in any closed system, entropy always increases over time. It's why ice melts in warm water but never spontaneously refreezes, why smoke disperses but never reforms into a neat plume. But here's the fascinating part. Entropy isn't just about things getting messier. It's about probability. Imagine a deck of cards fresh out of the box, perfectly ordered by suit and number. Shuffle it once and it's slightly disordered. Shuffle it 100 times, and the chances of it ever returning to that pristine order are practically zero. The universe works the same way. There are infinitely more ways for things to be disordered than ordered, so statistically, chaos wins. This statistical view of entropy was pioneered by Ludwig Boltzmann, a physicist who saw the universe as a game of probability at the atomic level. He realized that entropy isn't some mystical force, but simply the result of countless particles arranging themselves in the most likely, most disordered states. And here's where time enters the picture. Boltzmann suggested that the reason we perceive time moving forward, the reason we remember the past but not the future, is because entropy was lower in the past and higher in the future. In other words, time's arrow might just be the universe playing the odds, tumbling from order to disorder in a way that feels inevitable to us. But if entropy is just a numbers game, why does it feel so absolute? Why can't we ever unburn a piece of paper or unspill a glass of water? The answer lies in scale. At the microscopic level, particles are constantly moving in ways that could, in theory, reverse entropy. But the odds of trillions of atoms spontaneously coordinating to undo disorder are so vanishingly small that, for all practical purposes, it never happens. That's the illusion at work. What feels like an unbreakable law of time might just be the universe rolling a loaded dice, always landing on chaos. So if entropy is the hidden director of time's arrow, what does that say about the nature of reality itself? Could our entire experience of past, present, and future be a side effect of statistical inevitability? The more we examine this idea, the more questions arise, questions that take us beyond thermodynamics into the realms of quantum mechanics, cosmology, and even philosophy. If time's flow is just entropy in disguise, then what happens when we reach maximum disorder? Is the universe destined for an eternal, featureless equilibrium, or is there more to the story? The answers might lie in the most extreme corners of physics, where black holes warp space-time and quantum particles defy classical logic. But one thing's certain, entropy isn't just shuffling the cosmic deck. It might be dealing the cards for reality itself. The laws of physics play a strange game with time. At the smallest scales, particles dance to equations that treat past and future as interchangeable. Flip the sign on time in a quantum mechanical formula, and the math still holds perfectly. Electrons collide and rebound with no inherent preference for forward or reverse. Yet when we zoom out to the world we experience, time becomes a strict one-way street. Glasses shatter but never reassemble, candles melt but never reform. This stark contradiction between microscopic reversibility and macroscopic irreversibility lies at the heart of time's greatest illusion. Consider the Boltzmann brain paradox, a thought experiment that takes this tension to its logical extreme. Imagine a universe that's reached maximum entropy, a featureless soup of particles where disorder reigns supreme. In such a state, random fluctuations could theoretically conjure a self-aware brain, complete with false memories of an ordered past. If entropy creates time's arrow, then statistically, these phantom observers should outnumber beings like us who evolved in a low-entropy early universe. The unsettling implication: you might be such a fluctuation right now, imagining the past rather than remembering it. This paradox forces us to confront a radical possibility. What we call the past might not be an objective record, but a story stitched together by entropy's relentless march. When you recall your first birthday or last summer's vacation, you're not accessing some fixed timeline. You're relying on the fact that disordered systems leave traces. Memories are just physical imprints, like footprints in sand that only persist because the wind hasn't erased them yet. The future, by contrast, feels open because entropy hasn't sculpted its details. The cosmos amplifies this illusion on a grand scale. Look at the night sky, and you're seeing entropy's handiwork in the life cycles of stars. A young galaxy burns bright with hot, ordered stars, while an ancient one fades into scattered dwarfs and black holes. Even the cosmic microwave background, the faint glow of the Big Bang, shows us the universe in its most pristine, low-entropy state, like a snapshot of the wound-up spring that's been unwinding for billions of years. Yet if time's flow is just entropy in disguise, why does it feel so viscerally real? The answer might lie in our own biology. Your brain is a machine optimized for navigating an entropic world, wired to perceive cause before effect because that's how energy flows in our corner of the universe. But peel back the curtain and you'll find no cosmic clock ticking, just particles obeying timeless laws, while the arrow of time emerges from their collective drift toward disorder. The next time you feel the weight of a deadline or the nostalgia of a memory, remember, you might not be witnessing time itself, but the universe's most convincing magic trick. The Big Bang didn't just ignite the cosmos, it set the stage for the greatest magic trick of all, time itself. Picture the early universe not as a chaotic explosion, but as a flawlessly ordered symphony, a sea of particles so uniform and simple that its entropy was astonishingly low. This pristine starting point is the ultimate plot twist in our story of time's arrow. If entropy is the universe's way of keeping score, then the Big Bang handed us a ledger with just one entry: perfect order. From that moment onward, everything, every galaxy, every star, every breath has been riding the wave of increasing disorder, creating the illusion that time moves forward. This idea, known as the past hypothesis, suggests that time's arrow isn't built into the laws of physics, but emerges from the universe's initial conditions. Imagine a deck of cards perfectly stacked from ace to king. Shuffle it once and it's slightly disordered. Shuffle it 1,000 times and the original sequence becomes a distant memory. The universe works the same way. The Big Bang dealt us that pristine deck, and we've been watching it shuffle itself into chaos ever since. But here's the puzzle. Why did the universe start so orderly? Most possible initial states are messy and high entropy, like a deck already scrambled. The fact that our cosmos began in such a peculiar low entropy state is like winning the cosmic lottery, a freak accident that made time's arrow possible. Some physicists argue this isn't just luck. The conditions of the early universe might have been sculpted by deeper laws we don't yet understand. One provocative theory suggests that gravity, often seen as entropy's sidekick, could be the hidden architect. In the dense forge of the Big Bang, gravity may have imprinted order on the cosmos, like a potter shaping clay. As the universe expanded, that order unraveled, giving rise to the intricate structures we see today: galaxies, stars, and planets, all while entropy quietly climbed. This dance between gravity and disorder might be the secret script behind time's relentless forward march. But if our universe's low entropy beginning is what makes time feel real, what does that say about other possible universes? In a hypothetical multiverse, could some regions experience time backward, with entropy decreasing instead of increasing? It's not as far-fetched as it sounds. The equations of physics don't forbid it, they just make it wildly improbable. Imagine a bubble universe where shattered glasses spontaneously reassemble and memories form of events that haven't happened yet. To an observer inside, it would feel perfectly normal, just as our increasing entropy feels inevitable to us. This raises a haunting question. Is our experience of time just a fluke of cosmic geography, a quirk of where we happen to live in the grand scheme of reality? Or is there something deeper, a fundamental link between entropy and the very fabric of existence? As we peer deeper into the quantum realm or the mysteries of black holes, we might find clues that rewrite our understanding of time altogether. For now, the illusion holds, but the closer we look, the more the cosmic magician's sleight of hand begins to show. Time is the ultimate shapeshifter in physics. It bends, warps, and even loops in theory, yet stubbornly refuses to run backward in our daily lives. Take a simple game of pool. Watch two balls collide, and the event makes perfect sense whether you play the footage forward or reverse. The equations governing that collision, Newton's laws, don't care which way time flows. Zoom in further to the quantum realm, and the puzzle deepens. Particles like electrons obey Schrödinger's equation, a mathematical masterpiece that works just as elegantly whether time ticks forward or backward. So why does a shattered wine glass never leap back onto the table, reassembling itself into pristine crystal? The answer lies in the gap between microscopic symmetry and macroscopic irreversibility. At the smallest scales, physics is ambidextrous. It treats past and future as interchangeable. Scientists have even run experiments with particle accelerators where collisions look identical in reverse, like watching a fireworks display in rewind. But step back and the illusion crumbles. Smoke never undiffuses from a room. Coffee never unstirs itself from milk. This paradox is the heart of time's arrow. The laws are symmetric, but the outcomes are emphatically not. Enter statistics, the hidden choreographer of time's dance. While any single particle might reverse its path, the odds of trillions of particles all spontaneously coordinating to undo entropy are so vanishingly small that it might as well be impossible. Imagine trying to unshuffle a deck of cards by tossing them into the air. Technically possible, but you'd be waiting longer than the age of the universe for it to happen. Time's arrow isn't a law carved in stone. It's a numbers game where disorder always holds the winning hand. But here's where the plot thickens. If time's flow is just statistics at work, why does it feel so uniquely personal? Your memories, your sense of self, even your anticipation of the future, all seem to ride this one-way current. Consciousness might be the wild card in entropy's deck. Some theorists suggest that our awareness of time isn't just a passive observation but an active participant in the illusion. Like a spotlight in a dark theater, the mind could be selecting only the entropically plausible sequences, stitching them together into the story we call now. So is time's arrow a cosmic accident, or is there something deeper linking the physics of particles to the poetry of human experience? The equations don't say, but the mystery invites us to wonder whether the universe is playing a trick on physics itself, hiding the true nature of time behind the curtain of entropy. What if the flow of time isn't just a property of the universe, but a story your brain tells itself? Our experience of time, the steady tick of seconds, the unshakable sense of past and future, might be less about cosmic laws and more about the way consciousness stitches reality together. Think about the last time you were in a car accident or narrowly avoided one. In that split second, time seemed to stretch, every detail etching itself into your memory with unnatural clarity. That warping of subjective time reveals something profound. The clock in your mind doesn't always sync with the clocks on the wall. Neuroscientists call this time binding, the brain's ability to take disjointed sensory inputs and weave them into a seamless narrative. When you hear a knock at the door, see it swing open, and feel the breeze from outside, your brain doesn't process these events in perfect sequence. Instead, it retroactively assembles them into a coherent story, like a film editor splicing footage after the fact. This delay, usually imperceptible, creates the illusion of a smooth, flowing present. But under extreme stress or surprise, the curtain lifts. Time distorts because the brain scrambles to prioritize information, stretching moments to pack in more detail. Déjà vu offers another clue to time's illusion. That eerie sense of reliving a moment might occur when the brain's memory systems misfire, causing a new experience to feel like a recalled one. It's as if your internal timeline glitches, blurring the line between past and present. Philosophers like Daniel Dennett argue that these quirks expose time as a constructed reality, not an external river we float on, but a map the mind draws to navigate the world. Even our memories aren't pristine records. Each time you recall an event, you subtly rewrite it, like editing a document without saving the original. So is time's arrow just a byproduct of how our brains process chaos into order? Some theories suggest consciousness itself might be entropy's accomplice. The brain is a thermodynamic system, constantly dissipating energy to maintain its delicate order. As it filters the universe's noise into coherent perceptions, it could be mirroring entropy's one-way march, mistaking statistical inevitability for the flow of time. In this view, the past feels fixed because it's been etched into neural pathways, while the future feels open because your brain hasn't computed it yet. But what if consciousness isn't just observing time's illusion? What if it's amplifying it? Quantum models propose that observation itself might play a role in shaping reality, collapsing probabilities into definite events. Could our act of perceiving time be what makes it feel real? Alternative theories, like physicist Carlo Rovelli's timeless physics, suggest that without observers, the universe might not have a clear sequence of events at all. Time would be like a jumbled stack of snapshots, only arranged into order when a conscious mind flips through them. This raises a radical possibility. The arrow of time might not be woven into the fabric of the cosmos, but into the fabric of our perception. From the way neurons fire to the way we narrate our lives, every moment could be a collaboration between entropy's cold math and consciousness's warm interpretation. The next time you glance at a clock, consider this: you're not just measuring time. You might be creating it. Imagine the entire history of the universe from the Big Bang to this very moment laid out like frames in a film strip, where every event, every heartbeat, every supernova exists simultaneously in a frozen four-dimensional tapestry. This is the block universe theory, a radical view that past, present, and future aren't flowing but fixed, like landmarks on a map. Einstein's theory of relativity hinted at this possibility, showing that time isn't universal but elastic, stretching or compressing depending on how fast you're moving or how deep you are in a gravitational field. Two observers might disagree on the order of events, yet both be equally correct. A reality where now becomes as subjective as here. In this static block, your birth, your first steps, and even your last breath all exist eternally, like chapters in a book that's already been written. The catch: this clashes violently with how we experience life. Subjectively, time feels dynamic, a river carrying us from one moment to the next. But the block universe suggests that flow is an illusion, a trick of consciousness navigating the frozen landscape. Even entropy's arrow might just be a local phenomenon, a flicker of perception in a timeless whole. Quantum mechanics throws a wrench into this elegant picture. At subatomic scales, particles defy classical logic, existing in superpositions of multiple states until observed. Some interpretations suggest quantum events don't have definite outcomes until measured, implying the future isn't just unknown but genuinely unformed, a direct challenge to the block universe's predetermined structure. So is time's flow real or imagined? The answer might depend on where you're standing in the quantum fog where possibilities churn, or the relativistic cosmos where every when is just a coordinate. Quantum mechanics doesn't just bend the rules of time, it shatters them completely. At the subatomic level, particles exist in a surreal state of superposition, where they can occupy multiple positions or states simultaneously until observed. Think of Schrödinger's infamous cat, both alive and dead in its box until someone peeks inside. This isn't just a quirky thought experiment, it's a window into how time itself might lose all meaning in the quantum realm. If a particle can be in two places at once, or a cat both living and not, then what does before or after even mean? The Wheeler-DeWitt equation takes this confusion to its logical extreme. Derived from combining quantum mechanics with general relativity, this formula describes the universe as a static, timeless whole, a cosmic freeze frame where the variable for time simply vanishes. Imagine a grand cosmic clock that isn't ticking at all. In this view, time isn't just flexible, it's entirely absent from the fundamental equations, like a silent actor cut from the final script of reality. Yet here we are, watching the second-hand move, trapped in the illusion of progression. How does the universe bridge this gap between timeless equations and our relentless experience of moments passing? Quantum decoherence might hold the key. When a quantum system interacts with its environment like a particle bumping into air molecules or a detector, its superposition collapses into a single, measurable state. This process doesn't just create the appearance of definite outcomes, it could also stitch together the fabric of time itself. Picture a flipbook where each page is a quantum event, and decoherence is the thumb that animates them into motion. The now we experience might just be the universe resolving quantum ambiguities into a sequence we can comprehend. Entanglement adds another layer of strangeness. When particles become entangled, their properties link instantaneously across any distance, defying classical notions of cause and effect. If one particle's spin is measured as up, its partner instantly becomes down, even if they're light years apart. This spooky connection seems to ignore time entirely, as if the universe is playing a game where the rules don't include a clock. Some theorists suggest entanglement could be weaving hidden threads through spacetime, creating a network of correlations that transcend our linear experience of past and future. So where does entropy fit into this quantum puzzle? If time's arrow is just entropy's trick, does it also govern these microscopic ambiguities? Remarkably, quantum systems can sometimes appear to reverse entropy locally, like a scrambled egg briefly unmixing itself. But zoom out, and the larger trend toward disorder still holds. The quantum world's temporal free-for-all might just be the microscopic chaos that feeds the macroscopic arrow. Like a bustling city where individual pedestrians dart unpredictably, but the crowd as a whole flows in one direction, quantum weirdness could be the hidden steps in entropy's dance. Yet the deeper we dig, the more questions arise. If time emerges from quantum decoherence, does that mean reality is fundamentally timeless until observed? Could entropy be the glue that binds quantum possibilities into the timeline we recognize? The answers might lie in the unexplored frontier where quantum physics meets thermodynamics, a frontier where time itself could be the most ingenious illusion of all. Entropy isn't just a measure of disorder. It's the universe's silent timekeeper, ticking relentlessly forward with every scattered particle, every faded star, every breath exhaled into the void. Picture an antique clock slowly winding down, its gears grinding toward stillness. That's the cosmos in motion, a grand mechanism where entropy's rise is the only true marker of time's passage. The second law of thermodynamics spells it out plainly. In any closed system, disorder always increases. It's why ice melts in your drink but never spontaneously refreezes, why smoke disperses but never coils back into the cigarette. This law doesn't just describe change, it dictates the very direction of reality, turning entropy into the arrow that pierces every moment we experience. But here's the cosmic irony. Entropy's clock might be the only reason time feels real to us at all. Without this drive toward disorder, the universe would be a static tableau, a frozen snapshot where cause and effect blur into meaninglessness. Imagine a world where spilled milk could leap back into the glass, where shattered vases reassemble midair. Time's arrow would shatter, and with it, our ability to make sense of anything. The fact that we remember the past but not the future isn't just a quirk of biology. It's a consequence of entropy's one-way street. Our brains are wired to align with the universe's slide into chaos, stitching together memories along the grain of increasing disorder. Now fast forward trillions of years, stars have burned out, black holes have evaporated, and the cosmos has reached maximum entropy, a state physicists call heat death. Here, the universe is a lukewarm soup of evenly distributed particles where no energy can be harnessed, no structure can form, and no change can occur. The cosmic clock has finally wound down. In this bleak equilibrium, time loses all meaning. Without pockets of order to contrast with disorder, without systems to evolve or decay, the very concept of before and after dissolves. It's a chilling thought. Entropy doesn't just measure time, it might be the only thing that makes time measurable. Yet this raises a tantalizing question. Could the clock ever wind backward? Could entropy somehow decrease, reversing time's arrow? The equations of physics don't forbid it outright. They just make it absurdly improbable. Like shuffling a deck of cards into perfect order by random chance, a universe-scale entropy reversal would require statistical miracles beyond comprehension. But improbability isn't impossibility. Some theories, like the Big Bounce, suggest a cyclic universe where collapse and rebirth reset entropy's ledger. Others play with quantum fluctuations or multiverse scenarios where time's flow might vary. The truth is, we don't know if time's arrow is absolute or just a local quirk of our cosmic neighborhood. What we do know is this: Every moment you've ever lived, every memory you cherish, exists because entropy's clock keeps ticking. And that might be the most profound illusion of all, a universe conspiring to make us believe in time, when all it's really doing is counting down to stillness. Time travel has long been the playground of science fiction heroes flipping causality like a light switch, villains undoing history with the press of a button. But peel back the Hollywood gloss, and you'll find a universe far less forgiving. The laws of thermodynamics don't offer a rewind button. Sure, we've all seen those mesmerizing simulations where shattered glass reassembles or waves retreat back into a stone splash, microscopic reversals that tease the possibility of time running backward. And in labs, quantum systems occasionally pull off tiny entropy-defying feats, like a single particle briefly retracing its steps. But scale these up to the real world, and the numbers quickly spiral into impossibility. The odds of every air molecule in a room spontaneously converging into one corner are so vanishingly small that you'd need to wait many times the current age of the universe for it to happen. Once, this statistical lockstep is what makes global time reversal a myth. Even if every atom in your body momentarily aligned to reverse its path, the rest of the universe wouldn't oblige. Your coffee wouldn't unspill unless every scattered molecule coordinated with the table, the air, and the heat dissipating into the room, a cosmic orchestra with too many out-of-tune instruments. Yet there's a fascinating loophole buried in 19th century math. The Poincaré recurrence theorem suggests that given enough time, a closed system will eventually return to something close to its initial state. In a universe infinite in duration, every configuration of particles, no matter how improbable, would theoretically recur. Your atoms might rearrange into your childhood self, your first kiss replaying like a cosmic rerun. But enough time here isn't just long, it's ludicrous. For a system as complex as our universe, the recurrence time dwarfs the age of everything we know. It's like waiting for a monkey randomly typing on a keyboard to produce the complete works of Shakespeare, only to watch it immediately burn the manuscript and start over. Even if the math allows it, the practical reality renders it meaningless. So could entropy ever truly reset? Some cosmologists speculate about a big crunch, a scenario where the universe stops expanding and collapses back into a singularity, potentially rebooting the cosmic clock. In this fiery finale, gravity would overcome all other forces, compressing matter and energy back into a hot, dense state reminiscent of the Big Bang. If that happened, entropy might reset to zero, giving time a fresh arrow. But current evidence suggests our universe isn't headed for a crunch. Dark energy seems to be pushing expansion faster, making heat death, not rebirth, the more likely endgame. That leaves the multiverse as the wild card. If infinite alternate universes bubble into existence, each with its own laws and initial conditions, could some experience time in reverse? The equations don't rule it out. Picture a universe where entropy decreases, where smoke pours into cigarettes and sunlight flows back into stars. To an observer inside, it would feel perfectly normal, their brains wired to perceive decreasing disorder as forward. Our arrow of time might just be a quirk of our cosmic address, one thread in a tapestry of possibilities. The deeper we dig, the clearer it becomes. Time's flow isn't just a feature of reality, but a fragile artifact of how our particular universe unfolded. Whether through recurrence, crunch, or cosmic chance, the illusion holds for now. Imagine a cosmic quilt stitched together from countless universes, each patch with its own unique pattern of order and chaos. In this vast multiverse, entropy might not be a universal constant but a local flavor, some regions simmering in disorder while others cling to improbable order. Picture a mountain range where time's arrow points uphill in some valleys and downhill in others. This isn't just speculative fiction. It's a serious possibility within theories like eternal inflation, where new universes bubble into existence like boiling water, each inheriting slightly different physical laws. In some of these bubbles, entropy could decrease rather than increase, making time flow backward from our perspective. To an observer in such a universe, shattered glasses would spontaneously reassemble, and memories would form of events that haven't happened yet to them. It would feel as natural as our own forward march. The fractal analogy captures this beautifully. Zoom into a fractal pattern and you'll find smaller versions of the whole, each with its own intricate variations. The multiverse could be like that, a self-repeating tapestry where each universe, while unique, follows broader statistical rules. Most might be high-entropy wastelands, lifeless and static. A rare few, like ours, could be low-entropy anomalies where time's arrow emerges sharp and clear, allowing galaxies, life, and consciousness to flourish. This raises a provocative question. Was our universe's orderly beginning a cosmic accident, or is there some deeper principle favoring low-entropy beginnings? The anthropic principle offers one clue. We can only observe a universe capable of hosting observers, which requires the precise conditions for complexity to arise. But the philosophical stakes run even deeper. If our experience of time is just one variation in an infinite ensemble, what does that say about free will or the nature of reality? Are we merely passengers on entropy's one-way street, or does consciousness play some role in stitching time together? Some theories suggest that observers might be entropy's accomplices, collapsing quantum possibilities into the orderly sequences we call history. Others argue that time's flow is entirely perspectival, a side effect of our limited view of the multiverse's grand, timeless structure. As we peer beyond the edges of our cosmic neighborhood, the illusion of time grows ever more fragile. Whether rare fluke or inevitable outcome, our universe's entropic landscape might be just one note in a symphony of possibilities, a fleeting rhythm in the silence of eternity. If time's arrow is just entropy's sleight of hand, what does that mean for the choices we think we're making? The illusion of free will hinges on the belief that our decisions shape an open future, but if time's flow is just the universe shuffling toward disorder, are we truly the authors of our lives or merely spectators in a predetermined play? Philosophers have wrestled with this dilemma for centuries, but entropy adds a new twist. Imagine a game of dominoes where the tiles fall in a sequence dictated by statistical inevitability. You might feel like you're choosing which domino to tip first, but every collapse was set in motion the moment the initial conditions were arranged. Does that make your actions meaningless, or does the beauty lie in the fact that you're part of the pattern? This tension between determinism and agency echoes through two competing visions of time. Eternalism paints reality as a frozen block where past, present, and future coexist, every moment equally real, like frames in a film. In this view, your birth, your first heartbreak, and your last breath are all out there, fixed in the cosmic tapestry. Entropy's arrow becomes just a feature of how we navigate that tapestry, not a fundamental truth. Presentism, by contrast, insists that only the now exists, a fleeting spotlight moving through darkness. Here, entropy feels more visceral, a force carving the present from the fog of possibility. But both views struggle to explain why we remember the past and anticipate the future if time is either an illusion or a single point. The stakes couldn't be higher. If eternalism is correct, then your sense of self, the story you tell about who you are, is a thread woven into a larger design. Your struggles and triumphs are like notes in a symphony that's already been composed. Presentism offers a different solace. The universe is writing itself in real time, and your choices, however statistically improbable, add ink to the page. Entropy doesn't render life meaningless, it provides the canvas. Without the arrow of time, there would be no growth, no decay, no stakes, just an endless, featureless now. Cultures have long grappled with these ideas through myth and metaphor. Hinduism's cyclical time mirrors entropy's rise and fall, with universes breathing in and out. Indigenous Australian Dreamtime envisions a timeless realm where past and present merge. Even modern films like Tenet or Arrival play with entropy as narrative device, asking whether foreknowledge robs moments of their weight. The answer might lie in reframing the question. Instead of asking whether time's illusion diminishes our significance, consider this: perhaps the magic is in the trick itself. The universe convinces us the show is real, and for all practical purposes, that's enough. Your joy, your grief, your curiosity, they're no less profound because entropy set the stage. They're the sparks that light up the dark. Long before physicists grappled with entropy, ancient cultures were weaving tales of time as something far stranger than a straight arrow. The Hindu tradition speaks of endless cycles, universes breathing in and out like cosmic lungs, each inhalation a big bang, each exhalation a heat death, only to begin anew. Their concept of the Kalpa, a single day in the life of the god Brahma, spans 4.32 billion human years, mirroring the staggering scales of cosmological time. Contrast this with the Abrahamic traditions, where time marches linearly from Genesis to Revelation, a one-way journey toward divine judgment. These myths aren't just stories, they're early attempts to reconcile the same paradox that puzzles physicists today. Why does time feel so irreversible when the universe's laws seem indifferent to direction? Literature echoes this tension. T.S. Eliot's Four Quartets muses that time future is contained in time past, a poetic nod to entropy's hidden hand. Every moment, he suggests, is pregnant with all that came before and all that will follow, like a river carrying its own history downstream. Jorge Luis Borges took it further, imagining a library where every possible book exists simultaneously, a metaphor for the block universe where past and future are equally real. Even children's stories play with these ideas. Alice Through the Looking Glass turns time into a chessboard where the Red Queen runs faster just to stay in place, a sly commentary on how entropy forces complexity to evolve just to maintain order. Science fiction runs wild with entropy's narrative potential. In Kurt Vonnegut's Slaughterhouse-Five, aliens perceive time as a mountain range, all moments visible at once, with free will reduced to choosing which peaks to admire. Christopher Nolan's Tenet weaponizes entropy reversal, showing bullets snapping back into guns and explosions unfolding backward, though real physics would require rewriting every particle's path, not just a few. Even Doctor Who toys with the idea, portraying time as a wibbly-wobbly ball of stuff, where cause and effect occasionally untangle. These stories resonate because they tap into a deep truth. Our experience of time is fragile, a thin veneer over a far stranger reality. Now, cutting-edge research is catching up to these intuitions. Quantum gravity theorists like Carlo Rovelli propose that time emerges from the interactions of particles, like warmth emerging from friction. Experiments with entangled particles show correlations defying classical timelines, while simulations of black holes suggest entropy might encode information in ways that redefine causality. The line between myth and science blurs. Both are maps to the same uncharted territory, where time's arrow remains the ultimate enigma. Modern physics is tearing apart our classical understanding of time, revealing a reality far stranger than Einstein ever imagined. Take quantum gravity theories like loop quantum gravity or string theory. These frameworks suggest space-time might be pixelated at the smallest scales, a shimmering foam where past and future flicker like static on a screen. In this granular landscape, time could lose its smooth continuity, becoming more like a series of snapshots than a flowing river. Some models even propose that time emerges from the quantum entanglement of particles, as if the universe is stitching together moments like a cosmic loom. Recent experiments are putting these wild ideas to the test. Physicists have crafted ultra-precise quantum clocks to measure how time behaves near absolute zero, where entropy's grip loosens. Others are manipulating quantum systems to create localized entropy, decreases tiny pockets where time's arrow seems to wobble. Picture a nanoscale experiment where heat briefly flows from cold to hot, like a video played in reverse. These aren't violations of thermodynamics, but glimpses into the probabilistic nature of time's flow, where quantum weirdness briefly overrides macroscopic rules. Black holes, those cosmic maestros of entropy, add another layer of mystery. When matter crosses a black hole's event horizon, its information isn't destroyed but scrambled into a quantum fog on the surface, a concept called holography. This suggests that what we perceive as time's arrow might just be a holographic projection, a shadow play on the universe's boundary. Stephen Hawking's final papers hinted that black holes could encode time's passage in their evaporating radiation, turning entropy into a kind of cosmic film strip. Then there are time crystal structures that oscillate indefinitely without energy input, defying classical notions of equilibrium. Discovered in 2017, these bizarre quantum systems repeat their states in a way that mimics periodic motion, like a clock that ticks forever without winding. Some theorists argue time crystals could be windows into a deeper physics where time isn't fundamental but emergent, a side effect of quantum coherence. So where does this leave us? If time's arrow is just entropy's sleight of hand, what happens when we peer behind the curtain? Future experiments might probe the quantum entropy boundary with atom-scale heat engines or simulate black hole dynamics in lab-grown singularities. Controversial ideas like retrocausality, where future events influence the past, are gaining traction in quantum circles. One thing's certain: the more we learn, the less time feels like a river and more like a hall of mirrors, each reflection revealing a new facet of the illusion. The next breakthrough could come from a lab, a telescope, or equations scrawled on a chalkboard, but whenever it arrives, it'll rewrite not just physics, but our very sense of reality. What if mastering entropy could unlock technologies straight out of science fiction? Picture computers that don't just calculate but manipulate time's arrow itself. Processors tapping into entropy gradients like batteries drawing power from temperature differences. Researchers are already exploring thermodynamic computing, where information processing aligns with the natural flow of disorder, potentially revolutionizing energy efficiency. Imagine a chip that harnesses the subtle dance between order and chaos, turning the universe's tendency toward messiness into computational fuel. These machines wouldn't just solve problems, they'd ride the wave of time itself, blurring the line between physics and computation. Now stretch that idea to cosmology. If entropy shapes time's arrow, could we simulate universes with different thermodynamic rules? Advanced civilizations might one day craft entropy engines, creating localized regions where time flows backward or in loops. Think of a lab where scientists observe teacups spontaneously reassembling or memories forming before events occur. While this sounds like fantasy, experiments with isolated quantum systems already hint at tiny entropy reversals. Scale this up, and you're flirting with the ability to sculpt space-time itself, though the energy costs would dwarf anything humanity has ever produced. But with such power comes profound ethical dilemmas. If we could rewind entropy in a controlled area, would we undo accidents or erase entire histories? The butterfly effect would take on terrifying new dimensions. A single tweak to entropy's flow might cascade into unforeseen consequences, rewriting not just events but the very fabric of causality. And who gets to decide which timelines are correct? The moral weight of playing cosmic editor could make nuclear ethics look simple by comparison. Perhaps the deepest question isn't whether we'll crack entropy's code, but whether we should. Some illusions exist for a reason, like the magician's trick that delights precisely because we don't see the strings. If time's arrow is nature's greatest sleight of hand, revealing the mechanism might not dispel the mystery but deepen it. The more we learn, the clearer it becomes. Entropy isn't just a force to be harnessed. It's the stage on which reality performs, and we're both audience and actors, spellbound by the show. From the Big Bang's low entropy spark to the far future heat death, our journey through time's illusion has been a dance with disorder. We've seen how entropy weaves memory into being, how quantum flickers might stitch moments together, and how black holes twist the narrative. Yet for all our progress, the central riddle remains. Is time's flow a puzzle to solve or a story to embrace? The answer, like entropy itself, may lie in the asking. From the ink drop dissolving in water to the universe's slow march toward heat death, entropy has revealed itself as the silent choreographer of time's arrow. What began as a puzzle in steam engines has unraveled into a cosmic mystery, one that reshapes how we see everything from memories to black holes. The laws of physics may treat past and future as equals, but entropy's relentless rise paints the illusion of a one-way flow, stitching cause to effect, birth to decay, into the story we call time. This illusion runs deeper than physics. It's woven into the fabric of our consciousness. Every memory you cherish, every plan you make, exists because your brain evolved to navigate an entropic world. Even the universe's grand narrative, from the improbable order of the Big Bang to the scattered whispers of heat death, hinges on this single, slippery concept. Philosophers and physicists alike now grapple with a startling possibility. Time might not be fundamental at all, but a side effect of how we process disorder. Yet the most profound revelation isn't just about entropy, it's about perspective. If time's flow is an emergent trick, then reality itself becomes a kaleidoscope of viewpoints. To a quantum particle, the past might be as malleable as the future. To a black hole, entropy encodes information in ways that defy linearity. And to us, we're caught in the middle, our lives a fleeting spark between order and chaos, trying to decipher the magician's sleight of hand. Humanity's quest to understand time has always been a dance with the unknown. Ancient myths envisioned cycles and spirals. Einstein folded time into space. Now, quantum gravity theories suggest time might pixelate at the smallest scales. Each breakthrough doesn't simplify the mystery, it deepens it, revealing layers of elegance we're only beginning to glimpse. So the next time you glance at a clock, remember, you're not just measuring seconds. You're witnessing the universe's greatest performance, a show where entropy pulls the strings and time is the grand illusion. The curtain hasn't fallen yet, there are still wonders to uncover, from lab-made time crystals to the holographic codes of black holes. If this journey through cosmic mysteries has sparked your curiosity, hit like and subscribe. Together, let's keep unraveling the enigmas hidden in the fabric of reality.